Welcome to Kushar Academy, Unleashing Potential. Welcome to Chapter 1. This is an introduction part of force. Now we will be moving to Newton's law of motion. Newton, we have already seen that he had given gravity also, laws of gravity. Newton also gave three laws of motion, that how a particle or a moving object or a stationary object will behave under different circumstances. First law. Newton's first law states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. Means if there is no force, a body at rest will remain at rest, and if a body is moving in a constant velocity, it will continue to do the same if the net effect of an external force is zero. This is also known as inertia. So, the key point here is that if there is no net force acting on an object, each other, then the object will maintain a constant velocity, whether it is a zero or a constant velocity. This is what his first law is about. Second law of motion. The second law explains how the velocity of an object changes when it is subjected to an external force. First case, there was no force, then how it is going to change? Now, in the second law, he states that if there is an external force, how the motion of a body is going to change. The law defines a force to be equal to the change in momentum per change in time, or rate of change of momentum. Now, the momentum is given by P, generally given by P. Delta means change in momentum. What was the final momentum and what is the initial momentum? Now, first of all, what is momentum? Momentum is defined as m into v. Since velocity is a vector quantity, we are denoting by arrow overhead. Force is change of momentum, means if the final velocity was v, initial velocity was u, so this is the change in momentum by change in time. How much time did the body take to reach to v from u? Say it was time t, or the difference is written as delta t. So force is proportional to this quantity, which is written as delta p by delta t. The rate of change of momentum of a body is directly proportional to the force applied on it, and this change in momentum takes place in the direction of the applied force. Mathematically, it is written as F is proportional to change of momentum and how much time it took to change the momentum.
To Aristotle, this ball swinging around a string is in uniform circular motion. You can see it's moving at a constant speed around a simple circular path. Aristotle would have claimed that this object is not being accelerated at all because its speed isn't changing. It's neither speeding up nor slowing down. But Newton had a completely different view. Newton said that an object only changes its direction or its speed in the presence of a force. Well, the speed is constant, but the direction is constantly changing around and around as we go. Once up, once down, once left, once right, and all the way around the circle. Newton says this object is accelerating. And manifestly from the experiment it is, because I can feel the force I have to be putting through the string, keeping it swinging around. As soon as I let that force off, it just basically falls back down and stops moving. Newton's key insight was the understanding that acceleration is not just speeding up and slowing down, our everyday notion of accelerations, but also a change of direction of that motion at a constant speed. The second law tells us that this must be so, and I can understand completely and predict the motion of the ball swinging around the string just by using force equals mass times acceleration. I can even change the direction of the swing so that I'm swinging it over my head. As I move it around, if I want it to go faster, I have to put in more force, but when I regularize that force, it swings around at a constant speed, but the direction is continually changing due to that acceleration. Now, what would happen if the string were to break or I were to release the ball? That's when Newton's first law comes into play. In the absence of forces, the natural tendency of an object is to move in a straight line at a constant speed. And there it goes. It doesn't follow the arcing path that was impressed upon it by my accelerated motion. It flies off in a straight line at the position it was moving at the time that I let go of it.
Now, Newton's second law states about momentum, what we have already studied. Now, momentum is defined as P is equal to m into V, since it's a vector quantity. In serious unit, the SI unit of momentum will be, for the mass, it will be gram, for velocity, it will be centimeter per second. So, serious unit of momentum will be gram centimeter per second, and the SI unit will be kg meter per second. Kg is for mass, and meter per second is for velocity. When a force F is applied on the body for the time interval delta t, means for the time, short time, say I started applying force on the body at 10 a.m. sharp and I continue to apply the force till say 10:10, then the delta t will be 10:10 minus 10. That means 10 minutes. So this is delta t means for how much time the force was applied. So from the equation, the change in momentum will be written as delta P. Delta means change. Change of what? P. P is momentum. Change of momentum is change of mv, means change of mass into velocity. Now if we write mass cannot be changed, so delta P will be written as mass into change in velocity, what we had discussed in the earlier slide as well. Now we'll be deriving the equation how Newton came to F is equal to ma. This is the most popular equation that we have come across, and everyone remembers also F equals to ma. We said that force is proportional to the rate of change of momentum. So we are writing it as change of momentum is delta P, and rate means in how much time it was changed, it is delta T. So we'll be writing delta bracket P, substituting for P mv. So here. Now mass of an object for V, since many of the objects are moving less than the speed of the light, we see the mass is constant. So we can write it as m comes out. So it will be delta V by delta T, means change in velocity by change in time. Now what do we call change in velocity with change in time? This is known as acceleration. So substituting it with, so delta V delta T can be written as A. The equation comes as delta P by delta T as ma. Hence from the Newton's second law of motion, rate of change of momentum is given as ma, and since rate of change of momentum was known as force, force is ma. That means force is mass times acceleration. Now we'll be studying about the graph. Now acceleration force graph. So first of all we have to understand a graph name first of all. What the graph name says, it has two parts. One is acceleration, one is force. And what is in the first part? It is acceleration. So we have to remember here that whatever comes first has to be taken as y-axis, and whatever the word comes second is taken as x-axis. So in the y-axis we'll be writing acceleration, and in the x-axis we'll be writing force. So we know that if you read this graph, force is increasing from left to right. So increase in force will increase the velocity. That means increase in acceleration. That means the acceleration will also increase. The force is applied this much, the acceleration will be this. If force is applied more, the acceleration will be this. So this is the acceleration point, what we'll read here, and this is what we'll read here. Similarly, if you see acceleration mass graph, that means what? Acceleration has to be on the y-axis, mass has to be on the x-axis. So if a mass is increasing and the constant force is applied, this is for the constant force. So if a constant force is applied on a heavier object, it will accelerate slowly, and if it's applied on a lighter object, it will accelerate more. So we can see it will be inversely proportional. Less mass, more acceleration, more mass, less acceleration. So understood this graph? Acceleration mass graph, acceleration has to be on the y-axis, mass has to be on the x-axis, and it will be a decreasing graph. Now, CGS unit of force is known as times, and what vectors dyne force is mass into acceleration. So the dyne can be written as for mass 1 gram and for acceleration centimeter per second square. So one dyne is actually 1 gram into 1 centimeter per second square. So the one dyne is 1 gram centimeter per second square. In the SI unit, we call it as Newton. And what is the Newton's unit? For mass, it will be kg. For acceleration, it will be meter per second square. That means 1 Newton is actually 1 kg, 1 meter per second square. Now, if you wish to convert dynes to newtons, what will be 1 Newton can be written as 1000 kg means 10 to the power 3 grams in CGS units. Meter will be 10 square centimeters. So, in effect, 1 Newton will be 10 to the power 5 dynes because the unit on the right hand side is gram centimeter per second square. So, in effect, 1 Newton is 10 to the power 5 dynes. Third law of motion. For every action, there is an equal and opposite reaction. The statement means that in every interaction, there are pair of forces. Means if I'm pushing you, you are also pushing me. So there is a pair of forces acting on the two interacting objects. The statement means that in every interaction, there are pair of forces acting on the two interacting objects. For example, if you see here, a boy is pushing a rope which is in turn fixed to a wall. So boy is pushing the rope on the left direction. So rope will push boy on the right direction. And these are on the different bodies. Boy is pushing the rope on the left. Means the force on rope is towards left, and in turn the force on boy is on right. How do we explain this? See, suddenly if this becomes a slippery surface, so there is no force that the boy will be able to apply, and what will happen? For a fraction of a second, the rope is still applying a force and he will slip in the forward direction. If you see, the force in the weight machine or a force meter will read the same thing as 500 newtons, because pulling an elephant by 500 newtons, the elephant is also pulling me towards itself by same force, that is 500 newtons.
Welcome to the European Space Agency ESA. Newton came up with 3 laws of motion, laws that describe how forces and objects relate to each other. Alexander. We can see that they're floating. They're pushing against each other and move apart. That's an ISS battery and it looks heavy. That means it has a lot of mass, right? Once again, they're pushing against each other, but Alexander moves less. What we see this time is that for every action, there is an equal and opposite reaction. Newton's third law of motion. Alexander pushes against Pedro, action. This causes Pedro to move, reaction. At the same time, Pedro pushes against Alexander, action, causing Alexander to move in the opposite direction, reaction. And they moved an equal distance, action equal opposite reaction. The battery's mass is about 80 kilograms, so now the force is the same, but the mass is different. Remember Newton's second law of motion. Action and reaction are caused by the same forces, but they're expressed through different mass. Therefore, Alexander moves less. Let's see what the schools are up to. Here we go. This is like Pedro and Alexander on board the station. We add another girl and they don't travel as far. The force of throwing the ball makes her move backwards. A collision, that's a force. But do you know why only the guy in front moved? The students are arranged in what we call a Newton's cradle. Skater collides with the first student, action. The first student tries to move away from the skater, reaction, but can't. because there is another student in the way. So the force of the impact is passed through the next student and on to the end of the line. Then there's nothing stopping the last student, so off he goes. This is like the guys on the ice, only the last ball moves. And here the two balls are moving, but they don't seem to go as fast. This is because the same force is travelling through the cradle, but is expressed through twice the mass. As mass and acceleration are related, the two balls travel less than the single ball. The third law helps us in other areas too. Space vehicles use it to lift off. The air or gas is heated up and forced from the exhaust, action, and the reaction pushes the rocket up into space. Now you know about Newton's three laws of motion. Law 1 states that objects at rest or in motion stay that way unless a force acts on them. Law 2 says that the force is related to mass and acceleration. And Law 3 says that every action has an equal and opposite reaction.
Now for forces units, again a recap. 1 dyne is that force which when acting on a body of mass of 1 gram produces an acceleration of 1 centimeter per second squared. 1 Newton is similarly that force which when acting on a body of mass 1 kg produces an acceleration of 1 meter per second square in it. 1 Newton is 10 power 5 dynes, which we have seen earlier in the slide. Now there is some other forces as well which we study, which is gravitational units of forces. That means how much force the Earth gravity is applying on a mass of certain object. The force due to gravity on a body of mass m at a place where acceleration due to gravity is g is given as F equals mg. 1 kilogram force is the force by which Earth pulls a mass of 1 kilogram towards itself. So 1 kilogram force is what? The Earth attracts every body. Now if Earth is attracting 1 kg mass by some force, it is known as 1 kg force or 1 kg F. Now what is 1 kg F? 1 kg F can be written as mg, means mass is 1 kg, g is 9.8, so it comes as 9.8 newtons. Similarly, 1 gram force is a force by which Earth pulls a mass of 1 gram towards itself. 1 gf will be similarly 980 times. Now what is the difference between mass and weight?
Let's accept it. Most of us think that mass and weight are pretty much the same thing. Are they? No, they're not. There's a very simple way to understand the difference. Mass is simply the amount of matter that's present in the object. Now consider two situations. One in which an object is on the Earth, and second in which the same object is on the Moon. Will the mass of the object be different in these cases? To answer this question, we ask ourselves another simple question. Will the amount of matter present in the object be different in these cases? Absolutely not. The matter in the object is not changing at all, which is why the mass will be the same in each of the cases. The mass of an object remains constant no matter where it is placed. The standard metric unit of mass is the kilogram. Another concept we'd learnt about an object's mass was that it is a measure of its inertia. Greater the mass of an object, greater will be its inertia. Inertia is nothing but the tendency of an object to resist change in its state of motion. So now we have an idea about what mass is. But what's weight then? How do we understand the weight of an object? Mass is nothing but the measure of how much matter an object has. Weight is a measure of how strongly gravity pulls on that matter. It's the measurement of the gravitational pull of an object. Let's understand this using a simple example. Say there are two places, place A and place B, and there's an object of mass m. In place A, the pull of gravity is x units, and in place B, the pull of gravity is 2x units. Clearly, the pull of gravity is stronger at place B. Now understand this well. the mass of the object will be m at both the places, but the weight of the object will be greater at place B because the pull of gravity is stronger. As the gravity is twice as bigger, the weight of the object will be twice as much at place B as compared to place A. So the weight of an object is a measurement of gravitational force acting on it. How can we understand weight using a formula? We know the Newton's second law of motion, which says that the force acting on an object is the product of its mass and acceleration. When it's acceleration due to gravity, we can replace A with a lowercase g. This force due to gravity is nothing but the weight of the object. So if we consider the weight of an object to be uppercase W, we can rewrite this equation as W equals m times g. So the weight of an object is the product of its mass and acceleration due to gravity. What will be the SI unit of weight? Can you guess? It'll be the same as that of force, Newton. As the value of g at a particular place is constant, we can also say that the weight of the object is directly proportional to its mass. Here's the main takeaway from this video. The mass of an object remains constant everywhere, whereas its weight depends on the gravitational force at the location.
Equation of motion. Newton has given three equations. First, V is equal to U plus AT, S equals to UT plus half AT square, and V square is equal to U square plus 2AS. We'll be solving some questions based on these equations. Thank you for being part for introduction for forces.